Thank you for the introduction. I'm Chien from Latigo Biotherapeutics. Most of you probably know us as a NAV 1.8 company, but we also actually is exploring ASIC's role in pain. Today, I'm here to tell you about a tool peptide that we developed in-house called WRPRFa, which is an ASIC3-selective RFamide, and how we use this to study ASIC's roles properties. So first, let me share with you some background and how we discovered this peptide. ASICs are acid-sensing ion channels that are activated by acidic external pH stimulus. They form functional HOMO or heteromers. They allow mainly sodium to enter the cell to polarize the membrane potential. And most importantly for us at Latigo, they are found in pain-sensing DRG neurons. And we can see that in the current trace here, there are mainly three states here. So in pH, in regular pH, they start at a resting state, and upon acidic stimulus, they rapidly activate and then desensitize, and then until the pH goes back to the resting state. There are 5 ASIC isoforms, ASIC1 to ASIC5, with ASIC1 and 2 going through alternative splicing, giving 2 splice variants, 1A, 1B, 2A, and 2B. So there are total of these 7 different isoforms. And our RNA scope showed that multiple of these isoforms are present in the human DRG. Mainly ASIC1, 2, and 3 are the primary isoforms found. Majority of these cells, you can see in this pie chart, that are either ASIC1 only or ASIC1-3 co-expressing. And more importantly, they overlap with SDN10A or NAV1.8, as you heard many times in this symposium, which we now know is a marker of nociceptors. For the cell co-expressing ASIC1 and 3, we wonder if they are forming separate channels or heteromers, and what is the stoichiometry of these heteromers. So one way to identify these isoforms functionally is by their properties. These ASIC isoforms have distinct gating properties. ASIC1 desensitizes faster as the pH drops, whereas ASIC3 sort of remains similar throughout, maybe a little bit slower in the lower pH. ASIC2, on the other hand, has a big acidic shift in their activation pH, so you can see the pH stimulus we give here going down to pH 5 only starts to activate and then really activate at a much lower pH. But how do we differentiate them in tissues functionally? Since a majority of the population in DRG, as I showed, is ASIC1-3 double positive, we need a pharmacological tool to distinguish ASIC populations in functional studies. However, the tool, 2 sets of inhibitors of ASIC3 is pretty limited. APTX2 is a peptide inhibitor that's been reported to inhibit ASIC3, but also reported to inhibit NAV1.8, which is not ideal for our testing in pain-sensing neurons. We looked at all the published ASIC inhibitors, and here is a graph showing their selectivity on ASIC1 and ASIC3. So anything below this ASIC, this red diagonal line would be ASIC1 selective, and above would be ASIC3 selective. And as you can see, there really is a lack of inhibitors that's ASIC3 selective. So we turn our attention to the activators. ASIC is part of the larger ENaC-generative family, where small peptide RFamides have been shown to activate the channel. Here I'm showing FMRFa, and their activity on hydride sodium channel HiNaC, and so as FRFA, and their activity on ASIC1. And as you can sort of see here, that on the one on our case, their effect is only very modest. You can barely see any effect. So we look at RFamide that selectively target ASIC3 and found this peptide RPRFa, which is selectively slow the desensitization of ASIC3, but not so much in ASIC1. So, but this, we really would like this effect to be bigger in our functional study, so that we can easily assess it. And so we decided to conduct a SAR screen to sort of improve that peptide potency. And for that, we used the measurement of the current at 3 seconds, because the is ASIC3 quickly desensitized by 3 seconds into the stimulus. So we use the I 3 seconds over IT as a measurement, it's a quick measurement, and that's the measurement I'll use throughout this talk. So we conducted the screen using the Sophion two-patch system with variations of RPRF. And for the interest of time, I'm only showing a small panel of our screen. But what we found essentially is that by simply adding a tryptophan in front of the RPRF, making WRPRF, we get this massive, long-lasting, sustained current, slowing the sanitization that goes out for a very long time. So now we would like to characterize this peptide. How does WRPRF compare to RPRF? We did a concentration response curve from 0.3 micromolar all the way to 100 micromolar. What we found is that WRPRF has about 6.2 micromolar of EC50, whereas RPRF in our hand has about 66 micromolar of EC50. And as you can appreciate here, probably that we also have a higher maximum effect than 100 micromolar compared to WRPRF and RPRF. Then we tested whether increasing activity on ASIC3 reduces any selectivity when we test WRPRF on the other two major ASIC isoforms, ASIC1A and 2A. We did not observe any effect on desensitization on ASIC1 or ASIC2. One of the ways WRPRF works on the channel is by inducing an alkaline shift in activation pH 50. So here we tested ASIC3 with various pH stimulus from 7 all the way down to pH 3. By looking at pH 7 in between these two series of traces, you can already appreciate that WRPRF at 30 micromolar show a great increase in activation already. And this is the data here, so it does produce a really large shift of the activation pH 50. Then we would like to know exactly how long it takes for the peptide to fully bind to ASIC3. We did this by pulsing the untreated cells with WRPRF with various times pre-incubation, and then tested it with a fully bound channel and comparing the two sites of kernel, I3 over I6 sites. And what we found is that this activation is complete by about 10 seconds of pre-treatment of the peptide. Next, we measure the off rate of the peptide from the active or the closed state. First, we apply the peptide during the closed state for 20 seconds for the maximum amount of effect, and then we just stimulate the channel again, and then to see how if the peptide comes off during the activated state at all. So at first, you can see the channel desensitized, likely due to some unbound channel desensitizing, but then we can see that this sustained current was really long-lasting for up to a minute in most of our testing. We did not hold the cell at pH 6.3 for longer than 1 minute because it's not really well tolerated by the tech cell. But in some of our testing, we can have this sustained current lasting more than 3 minutes. On the other hand, when we perform the washout during the resting pH, so this was done at pH 8, so every 20 seconds, we'll apply the peptide for 20 seconds for the maximum effect, and then every 20 seconds, we'll give a testing pulse to see how much peptide is left on the channel while continuously washing out the peptide using our conditioning pH. And what we found is that the washout can be completed in 3 minutes. So far, we have only looked at WRPRF binding in the resting state, but what about in activated state or near the next stage does our peptide bind? So we applied WRPRF simultaneously as we activate the pH, and so that there is only a minimal effect in comparison to when we apply it during the closed state. This could mean that WRPRF doesn't really want to bind in the activated state, or it doesn't have enough time because this ASIC3 desensitized so quickly that there's no time for the peptide to bind during the activated state. Similarly, we apply the peptide during the desensitized phase of ASIC3, so we hold it during the desensitizing pH and apply the peptide again during this portion of the curve, and then stimulate again. And again, we found that there is only minimal effect, so that we conclude that WRPRF only prefers to bind to the closed state of ASIC3 and then stabilizes it in the open state when it's activated. Now we have some basic characterization of the peptide. We did another set of experiments to understand the binding site of our peptide. In our screen, the SAR told us that the two cationic arginine in WRPRF were important. So we looked for constant charges using the ASIC1A crystal structure. We found for counter charges, so what we found is these two pairs of glutamate E378, E416, E78 and E421, facing into the central vestibule where RFamide has been shown to bind into ASICs in our observed before. And they are close to the beta-11-12 linker, which is the molecular clutch that controls the desensitization process of ASICs. So this is a likely spot for the peptide to bind to impinge on the desensitization process. We neutralize these charges by mutating the E to Q, and the upper two pair, E378Q and E416Q, didn't really show any decrease in sensitivity to our peptide. So as you can see, the current remain having long, big sustained curve after the mutations. On the other hand, the lower pair, E78Q, showed a really dramatic increase with WRPRF treatment. So WRPRF is still effective, but actually the small current baseline suggests that there is an acidic shift in their activation. And when we look at E421Q, we saw a dramatic effect showing loss of effect of our peptide in this mutant. So we look closer at the E78Q to see whether it is indeed there is a shift in their pH activation. And so indeed that's what we found. So as you can see here on the right, so comparing to wild type, actually there is a more acidic shift in their pH 50 to closer to pH 6. And when we apply WRPF, they actually restore this to the same level as the wild type, so they start to activate around pH 7, just like we saw in the wild type channel. And we look at the peptide's effect on these 4-point mutants again, and while E378, E416, the upper pair show minimal shift in their potency, E78 has a significant left shift in the peptide binding, while the E421, that's the one that lost the effect, has a significant right shift. So for our next analysis, we actually pick E78 for our next analysis because the other one, E421, the shift is so great that we cannot get a reliable number for our next set of experiment. So to orient WRPRF in this region, we use the double mutant cycle approach to determine the coupling between either the second or the fourth arginine to the lower glutamate pair. We selectively mutated these two arginine to ADMA or isoleucine to make WRPADMA-FA and WIPRFA from our SAR screen. So what double mutant cycle is to look at the potency shift from single mutant of peptide or the single mutant of the glutamate that we mutated. And if the residues are uncoupled, then the potency shift of the double mutant should be additive or the same as the product of the two single mutants with the coupling coefficient of 1. The two mutants, if they are coupled, then the shift will be greater or less than the combination of single. And this was calculated by multiplying the wild type and double mutants over the two single mutants combined. So potency shift of the double mutant of E78Q and WIPRF pair was actually has coefficient of 2.09, suggesting that the coupling is there, but not as great as when we look at the next pair, E78Q and the second arginine mutation, WRPRFa, where we have the coefficient of 6.99, suggesting that we think that this arginine here, site 2 arginine, is the one interacting with the lower 2 pair. Next, we want to know how WRPRF how it affects the steady state desensitization of ASIC3. What steady state desensitization, how does it look like in ASIC? So here I am lowering the preconditioning pH from pH 8 all the way down to 6.8. And you can see that when we give an acidic stimulus, the current actually diminishes as we go down the conditioning pH. So it's completely gone by pH 7 in this case. So we compare this to when we treated the cell with WRPRF. So what it does is that when we apply WRPRF, it also has this left shift of activation, so the channel starts to open at around 7.4, so creating this window current. So when we did our test pulse, we are actually measuring the difference between the channel that are conducting acute desensitization and as well as the steady state desensitization. What we found is that this pH, there's not much of a pH shift between the two, but when we look at something like the conditioning pH 7, we found that actually if there are no, this is the testing pH is testing of the combination of both acute desensitization and steady state desensitization. So how much channel is actually desensitized at this point. And what we found is that because these two are not edited comparing to the original testing pH, so we conclude that some channel, a fraction of the channel were desensitized from the resting state, suggesting the channel can enter the desensitization directly from resting. So giving rise to yeah. Finally, I would like to show you a phenomenon that we observed during our activation pH 50 experiment, and that is called tachyphylaxis. During our measurement of pH 50, we noticed that after pH 4 and at pH 3, the current is now restored to their original amplitude after multiple stimulation. This reminds us of the ASIC1 tachyphylaxis shown here, that when you have repetitive acidic stimulus, the current rapidly diminishes, and this part of the current is irrecoverable. So we want to see if ASIC3 does indeed go through tachyphylaxis, which has never been shown before, and if our peptide WRPRFa has any effect on this process. So indeed here, I'm showing for the first time that ASIC3, if we repeatedly simulate the channel with pH 4 pulses, the current diminishes until it's complete, and this process is irrecoverable in our end. And more interestingly, when we apply WRPRF before we do this experiment, this process actually accelerated. We then wonder if ASIC3 tachyphylaxis go through the same biophysical process as ASIC1. ASIC1 tachyphylaxis is due to the time in open state, and prolonged single acidic stimulation has not been shown to accelerate ASIC1 tachyphylaxis. Meaning, no matter how long we hold ASIC1 in the acidic stimulus that induces tachyphylaxis, the amount of the current loss is the same each time. So we wanted to see whether it's true in ASIC3. So what we did is we give a non-tachyphylaxis reducing pH first, and then we hold the channel at the tachyphylaxis reducing pH 4, for a different amount of time. And if it's the same process as the ASIC1 tachyphylaxis, then the second pulse, test pulse at pH 6.3 will be the same each time. However, as you can see here, when we go from 5 seconds, 10 seconds, and 30 seconds, this is not the case, as the currents continue to diminish and we hold the channel at the lower pH environment. And again, WRPRF accelerated this process. So this suggests that this could be a distinct process from the ASIC1 tachyphylaxis. So in summary, I think I show you that WRPRF is a more potent and effective ASIC3 modulator than RPRF, and the way it works is that it strongly stabilizes ASIC3 in active state. And I showed you that ASIC3 can undergo tachyphylaxis in the very low pH condition. With that, I would like to thank my colleagues at Latigo, Nian Du and Shang. He did the bulk work of the ACR screen on Chien, and Victoria Zhang, she is now a grad student at Johns Hopkins, was the first person who did all the pioneering work with John Gilbert on this peptide. Oh, and also I'd like to thank James Griffin for making of the many peptides that we use in the screen, and Sophion for their support on this peptide. All right, and then thank you.
Really cool or powerful activator. And I was wondering, in the binding site that you think you found for this, is it a hotspot for other modulators of the Degenerin ENaC superfamily or ASICs generally?
Right, so the binding site that I showed you was found away from similar for ASICs in the family, but actually for other RFamide like the high-run sodium channel, actually the RFamide binding site is in a completely different position of the channel. So they both, the ENaCs are all modulated by I wouldn't say all, maybe not all, but they're modulated by the RFamide, but the binding sites are actually very different.
Huh. That's wild.